Well, hello everybody, I am Gael Ramos, and this is my project, named Gaunlet. So I was researching into the different people and different populations, just taking a look into consideration accidents and hand disabilities. There are more than 3 million people in the USA that suffer from one of these problems of hand disabilities, hand problems, and different things. And this is a very important problem to acknowledge, to see. Because they not only cause joint pain, muscle weakness, diseases, with strength, and other things, but also since the hands are over very important for our face to interact with our environment, they're very important for the daily uses of every people, every person. So these cases they often require therapy and reconditioning. Yeah, this can be either harmful, expensive, and very time consuming. And in many events that can be extreme, cause long-lasting recoveries or permanent damage to these areas. They are not helpful to someone have a daily life that is usable and good. So I wanted to make something out of this, and I want to help people. So I had a goal for this. And it was first to create a device to call six different individuals, to vary from hand disabilities, or hand problems related to motor skills, or hand motion. This in order to help them have a daily life that is better, more and just easier. And my second goal is to promote the research on different prosthetic connections of the body to the brain and the brain to different parts. This to assist the general industry with information or just be able to make different prototypes that could improve other ideas into how to make prosthetics. So, in order to achieve my goal, I needed to do research. And since I'm trying to agree the hand, I'm just trying to know first how the hand actually acts. So first we're gonna go get into the bone. The bone is a structure of the hand. So what we're going to replicate is five different sets of bones. First, the phalanges. The phalanges are what we can call the different fingers. They have the fingers, and they have different sets of small bones that connect each other. Then we have also the metacarpals. There we can call it the palm, the dorsal of the palm. This is more like the base thing that it connects. We have the carpals. The carpals are located around your breast, and they are very useful to support. And then first, you have the radius and the ulna. The radius is connected usually along the tongue. So this can be located in the tongue section. And then in the opposite side is the ulna. Since the bones are the structure head to support tension and compression, they are very useful to our body. Then we have the muscle. The muscle is the part that gives motion to different parts of the body, especially the hand. So there are different muscles that either move the breast, the whole palm, the whole forearm. But what we use in our purposes is two different sets, the flexor and the extensors. And as the name says, they either extend or flex. So the extensors are located on the dorsal of the palm, and the forearm are along the palm. And like this, the extensors make of waves extend, and reflexors flex along all the palm. And since this, the movement of the hand usually can cause different strength issues, and they can cause many different problems. These are very important to analyze and see how we can relate them in order to track them very easily. Related to this, we have the tendons. A little difference in tendons and ligaments is that ligaments are connected into bone to bone, and tendons are from muscle to bone. So that's why we can notice first the tendons. These tendons are located are for the same pair at the muscles, so they call the extensor and flexor tendon. These use and make the same movements as the adductor parents. They can be either extend or flex the fingers. And these are very important because we need to replicate them in order to imitate different movements and different muscles. And then finally, a very important part is the nerves. Nerves is the central way of communication from the brain all the way from the spine to the different parts of the body. and in our case, the hand. We have three different nerves having that knowledge. There is the radial nerve, ulnar nerve, and medial nerve. We have the ulnar and medial. The ulnar is located along the ulnar bone and located all the way from the pinky to the middle finger. And then we have the medial nerve. The medial nerve controls the signals again from the middle finger to the thumb. And then on the opposite side, you have the radial nerve. Radial nerve is on the dorsal of the hand. And just with many other fingers from the thumb all the way to the different fingers of the pinky. This is important because the nerves send information from the brain to muscles, bones, ligaments, and everything. And this is a very important part that we will not use actively, but passively it will be very, very important. So, in order to make this possible, we use different materials. There are strings, 9-volt batteries, servo motors, 3D equipment, EMG muscle sensors, gloves, microcontroller, power cable, and cables. So first, to be able to make this prototype, we're going to say first say something. That is, what it is an EMG sensor. So an electromagnet or EMG sensor basically detects electrical activity from a muscle. So muscles are composed of fibers. So what we call bicep or tricep. It's just a group of different fibers located along the bicep or the tricep. And a very important way that this act is that they do not act by ranges. So obviously they are ranges, but they do not act all together. So there can be like many fibers that are completely flat, and many others that will be doing nothing. And this is a problem because in order to have a good reading, we need an average, not different disturbances, in where there are different gaps and different voids, different gaps, different values. So we need to make it all into one single thing. And in this, you will come the EMG sensor. This sensor, what it makes is get the raw EMG in the red lines. So because it spikes different things, this is because of different voids. Sometimes are being detected by the sensor. So with this raw EMG, it generates an average of this activity and creates an EMG envelope. That's basically all of this compressed into one single line that is easier to enter with for machines and for and this is very, very useful. So we have a good useful information to acknowledge and to see forward. So as an engineering project, it's very extensive and a different procedure. But this can be divided into three different things: the information processing, the control transformation, and the mechanical implementation. First, we're studying the information processing. Physical information. It starts with the EMG sensors. So locating two different electrodes, the red one and the blue one in the style and the white one, and the blue one. Then it is not damage, but it's in a part near a bone to have like a graph and that is information so we can make an average. And then as you can see to the right, this number is what this sensor actually sends into the computer and we send it to our brain. So this is actually what we're receiving. And with this information, we'll be able to make an educated guess on how the hand is being moved or what state it is, and replicate that with our skills and with our technology. Then jumping to the next part, have the controller transformation. So as I mentioned before, there's an EMG controller that's information from the muscles all the way to this that we can call the brain. You can see the right, we have the code. This code is basically what controls the fingers. And in order to explain it, we can say it as a role. What I make over here is create a start and an end. The start can be the hand being open and the end the hand being closed. and I attach different values of how the motors need to be at those different parts. They can be either at zero when it is open, and at 170, that is like the max, and being closed, and all different values. So with these two different sets, what I make is okay, taking the UG value, I see that this UG is at exactly middle of between these 2 points. So I take these 2 points, get the middle value, and get those values for the motors, and send it into the all different figures that are being used. And do the same thing if the value is in the one of the part, 1/8 of the graph, or minus 1/8, or different things. So with this, we're able to have a whole spectrum of different ranges into we can move over the value and our motors to be able to replicate or mimic the hand. And having this value, we jump all the way to the biomechanic implementation. So basically here, we go as just implement biomechanics into a mechanical way. So you see, we need to transform this within the figure 10 and joints and create this like, movement to the actual movement biomechanic. So taking rubber bands and placing them within the phalanges and on different bones of each phalangeal good movement in order to have a good extensive movement. And using the motor, we usually use a cable in order to flex. So each time we flex, we force the figure to go and be able to close it. And then once we lose that force, slowly the rubber bands will get the figure into their original state. And this is actually how it works. So our results, you can see over here, is we were able to measure different data with the values, and we also were able to create a prototype that we were able to analyze and see how they interacted with our head. So gain this information, we were able to make a successful prototype and to gather this information. And we conclude that in conclusion, it was possible to recognize capable of mimicking the hand gestures. But the problem is that the capabilities for being a daily usage things are very limited because of battery, of size, and everything. However, the capabilities of assisting with recoveries are still pending into being completely understood because being more like a standing tool, it can be used to recover the different patients and be able to have a better strength and be able to act and get different recoveries to gain some functionality. And even more, and even better thing that we can use this prototype is for assisting into prototype and prosthetic information developing. So with this, we were able to use different information to analyze how the emotions work and how we can use that in order to make better prosthetics and merge prosthetics. So for the future, I want us to improve into this area of researching and investing into prosthetics. And I was able and want to use different types of information to make the prototype and the prosthetics. For example, using brain signals. These brain signals will only be faster to read, not faster, we're able to read precisely, but it will help not only for prosthetics, because having a prosthetic hand like the brain signals to actually move it has many different implications. For example, different diseases, as it can be Alzheimer or loss of memory, like Alzheimer, both from accidents, not by diseases, or for example, in a paraplegic individuals, this could be very useful because training and actually using your brain for moving different things, we were able to analyze better how the neurons work and how they connect and create different pathways for the neurons. And with this, we can be able to invest and have better technologies in order to recover our brain neurons and connections. So, thank you for watching, and this is everything. Goodbye.